Today we are going to solve ordinary differential equations symbolically in MATLAB. Not every ODE has an analytical solution, but for simple cases, you may want to try this function, dsolve. It returns the symbolic solution of ODEs, and the syntax is simple. You just write the equations. Also notice that writing equations in a string format is not recommended, so I only focus on the correct way of defining equations. Let's start with this example. Y prime equals y squared. Step 1. Defining symbolic variables. Y is a function of, let's say, t, and this is how to define t as a symbolic variable and y as a symbolic function of t. Step 2. Write the equation. The derivatives are defined using diff function, so my equation is diff of y equals to y squared. By default, diff of y means the first order differentiation of y with respect to t, but we could also specify the order of differentiation and the independent variable explicitly. It won't make any difference. Step 3. Run dsolve for your equation. And this is the solution we expected. I change my equation a little and solve it in a script. Here again, those 3 steps are taken. Notice that this is the assignment symbol. It means this expression is stored inside this variable, but this symbol is the equality sign, meaning the left and right expressions are equal. Notice a little modification can lead to big variations in the solution. I also want to mention that usually we are not interested in these constant solutions, so we ignore them. Solving a system of differential equations. Suppose I have these 2 equations in which x and y are both functions of t. Again, I take those 3 steps. I define my symbolic variables. Then I define the equations. Then I find the solution using dsolve. Solve.x and solve.y show me the results. To solve an initial value problem or boundary value problem, we just add the initial or boundary conditions to the end of our dsolve command. Suppose I have this equation and the initial condition is 3. I can easily plot the solution using fplot command. As the last example, let's solve this ODE. It is a second order boundary value problem. I define y as a function of x and then I write the equation. Notice how I wrote the second order differentiation term. Solving this equation returns this answer. Notice that we have an arbitrary constant in our answer, so the answer is not unique. In contrast to the initial value problems, which usually have a unique answer, the boundary value problems that arise in practice may have no solution, a unique solution, or an infinite number of solutions. Before ending this tutorial, I just want to mention that most of the differential equations have no explicit solution. So if you couldn't solve them analytically, you must go for numerical solutions, which I'm going to cover in my forthcoming tutorial. So subscribe to my channel and like this video. Bye bye.